Yeah, thank you very much, Alexander-san. Nice introduction. Yeah, I'm very happy to have this opportunity to talk about our recent work on Mixed-Anion compounds. So can I share the screen? Yes, it's
Yes, it
okay.
works.
Works. Okay. Yeah. All right. Once again, thank you very much. So I'm okay. Going to talk about recent progresses and the future directions of Mixed-Anion compounds. But some of you might not be familiar with Mixed-Anion compounds. So in the beginning, I'd like to discuss the brief introduction. Okay, then we move on to our recent topics. By the way, you know my connection to Russia started since 20 years ago when Alexander Vasilyev visited professor in University of Tokyo, where I was a research associate. Then I had the opportunity to visit Moscow State University. Actually, in Moscow State University, there was a conference on magnetisms, and where I met John Goodenough and his wife. So this is nearly 25 years ago. Then later on, I had a chance to visit to St. Petersburg. That is for the conference of International Conference on Reactivity of Solid, organized by Evgeny Antipov. Then I had a nice photo with Ken Poppenmeyer. Anyway, I I'm very happy to have this opportunities. So today, my talk will be organized as follows. As I said, I'd like to briefly introduce what is Mixed-Anion compounds. Then I'd like to focus, on how to control bonds, how to create bonds to get some interesting structures, some interesting properties. Then I pick up these two topics. Okay. Then, as you might know, the oxides are very well known. And actually, this was because of the stability of oxide, that there are many materials found and many compounds show interesting properties from ancient to modern. And for example, this barium titanate, famous ferroelectric materials, and this is zirconia oxides, solid oxide fuel cells, and this is battery. And because thanks to many functions, we can have many benefits from for our lives. And also, this feature, the nice oxide material, can be benefited by this easy to prepare features. So even non-chemist or non-solid chemist can prepare many materials, okay, by just heat and beat processes. But disadvantage of oxide material is that you cannot have the freedom in terms of the ligands. So all the metals, some transition metals, are coordinated by oxygens. So this coordination geometry can be used as a Lego bricks. Then you can combine, integrate these Lego bricks to form some crystal structures. Okay, this is maybe the limitation for oxide materials in terms of structure diversity as well as the functional diversities. However, situation can be greatly changed when you partly replace oxide anion by other anions such as nitrile anion. Then you can have variety of new geometries. Okay. Then there are several parameters of an ion, such as the charge or compressibility, polarizability, electronegativity. Okay. By utilizing these anion derived parameters, we may be able to control structures and functions. Okay. So that is the essence. So one of the important discovery I'd like to show as an introduction is this one. So this is, as I said, the famous ferroelectric material, oxide material. But by reacting this material, powder sample with calcium hydride at this temperature in a no, in vacuum, we are able to partly replace some of the oxygen ligands, these red guys, by hydride ligand. Then you can have the color change from white to blue. Okay, so actually this is nothing but electron dopings. So this show metallic behaviors. Then of course the oxide is very stable. Then you can use oxide as a coffee cup and so on. But what happens when you have a hydride inside a coffee cup? Then maybe you don't want to have a coffee with this. However, you can use this, active nature of the hydride or hydride anion to functionalize this new type of oxide materials or oxyhydride materials. In fact, the oxide are very stable and very difficult to make some reactions with some gases. But this oxyhydride has ability to cleave the small molecules. For example, in this case, the hydrogen molecules in the atmosphere can be cleaved to make some anion exchange reactions at this temperature. More surprisingly, this material can cleave the triple bond of nitrogen. Okay, so in this reaction conditions, actually nitrogen triple bond can be cleaved. Actually, this oxyhydride is changed into the nitrile materials. Typically, oxynitrile material can be formed by flowing ammonia gas at very high temperature, such as 1000 degrees C. But ammonia is very toxic. But in this case, you don't need to use ammonia gas, but very, very inert nitrogen gas can be cleaved to form oxynitrile materials. Okay, but when we flow this H2 gas and N2 gas together at some temperatures, such as 400 degrees C, we are able to see that the generation of ammonia, actually this material, this oxyhydride material, can be the active catalyst for ammonia synthesis catalyst. Okay. Without hydride inside material, there is no ammonia generated, as you can see this graph. But once you introduce hydride into oxide, this material can generate ammonia gas. So this is the nice, catalytic materials. The amazing thing is that the titanium is not regarded as a good catalyst for ammonia synthesis because of the very, very high, formation enthalpy for titanium nitride. Okay, titanium nitride is very famous coating devices with melting temperature of more than 2000 degrees C. Okay, but as you can, so in this regard, the titanium is not active for ammonia. So actually, this volcano plot for nitride formations, titanium is located at far beyond this graph, something here. But introduction of hydride into material, titanium oxide material, can drastically change the scaling rules for catalytic activities. So I think this is very nice example that the introduction of the non-oxide anion or mild anion can drastically change the property, generate properties. So oxide cannot be, in this case, the catalyst for ammonia synthesis, but oxyhydride can do this. All right. So it is more than 8 years ago. I was very fortunate to lead these many people, Japanese researchers, to have this Mixed-Anion project. And since that time, so since 2016, the number of the publication containing Mixed-Anion increases, like you can see in this graph. Okay. And now we are extending this type of big project into international one. Luckily enough, actually, I recently got the so-called Aspire project. This is funded by JST, Japanese agencies. And now we have this international collaboration to make some exchange of students and professors and so on to make Mixed-Anion researches forwards. Okay. But so this one, maybe I strongly recommend you to take a look at this Mixed-Anion textbook. You can have the how to this actually contains some essences of the Mixed-Anion compounds in terms of synthesis, structural characterizations, or compositional characterizations, chemical property, and physical properties. Okay. But maybe for the brief look at the Mixed-Anion, that this can be more compact version of this Mixed-Anion review articles. So, for example, this is the figure 1 of the this Mixed-Anion review paper in this article. And for example, by replacing oxide anion ligand by nitride, you are able to greatly tune the crystal field splittings. Okay, it is similar to what coordination chemists have been working on, but you can do this in extended uh, solid materials. And also by replacing some anions for oxide material, you are able to control, or particularly in this case, you can reduce the band gap to make the material responsible for visible light, for example. And also, you can have new degree of freedom, such as cis and trans in this case. Also, you can reduce the symmetry. So octahedral symmetry is very highly, symmetric. But by replacing like this and that, you can have different symmetry, like C4 and C3 symmetries. Of course, the bonding differentiation is important parameters. So here I emphasize the ionicity and covalency that can be tuned by changing the ions. Okay, and actually such a difference in the anionic species is pretty important to control the physical properties. Actually, actually oxide material is very ionic, very hard anions. But maybe other anions such as maybe sulfur or chlorine or maybe hydride are very soft anions. The softness means that this anion is more responsive to external stimuli such as temperature or some pressures. So this can give much more freedom or extensive opportunity to give change the bonding natures or bond structures. Okay. And this is this cartoon shows the difference of the reactivity. So as I showed in the previous slides, the hydride is very reactive to the outer atmosphere, or hydride can migrate through the lattices. So this can be nice anionic conductors. Two-dimensionality, very important for physical properties. And most of today, my talk is focusing on the multiple anions, but the single anions. But here, you can extend the mixed anion strategy to include the molecular anions such as O2 minus or BH4 minus and so forth. Right. So from now on, I'd like to talk about these 4 examples, starting from these iron oxyfluoride materials. Actually, this is the unpublished work, but this is based on nice collaboration with Professor Kengo Oka at Kinda University, who made these new materials. But this material is basically described by the Ludreston Popper type layer perovskite. It is the case of double layer systems. Okay. Here, important thing is that the oxide and fluoride are ordered, not disordered. So this fluoride, which is shown in red, is located preferentially at the apical site. And the equatorial site are occupied by oxide, and this bridging site also occupied by by oxide anions. So here, fluoride are located exclusively at these positions. Okay. Apart from this, it is the simple loadless Popper type perovskite. In any case, the another important key, component is that lead. Lead is very famous material, cations, which contain the lone pair electrons. So it can be stereochemical active. As I said in the previous slide, some anions have, the different chemical bondings. So when you combine such a mixed anion feature with the cation containing lone pair electrons, you can have much more interesting phenomena, which you will see later. Okay. But anyway, this material has interesting structure property or structure phase transitions. So this shows high temperature phase. Actually, this contain octahedral rotations. Okay, so the superstructure is obtained. But anyway, this material has this type of octahedral tiltings. But below 400 Kelvin, at 400 Kelvin, the structure phase transition occur from this crystal structure to this crystal structure. And upon this structure phase transition, the superstructure vanishes. But as you can see, that here octahedral shape are pretty, distorted. The high temperature, of course, the high temperature is also distorted, but much less. Okay. But here, there's a large shift of the central iron species, which is trivalent anyway. But a large shift is, luminescence of the ferroelectric transitions. In fact, each layer is ferroelectric, the polar structures. But neighboring layer have different the polar directions. So actually, this material is not polar. But this structure phase transition from this high temperature phase to low temperature phase is similar to the transition you can see in like a lead titanate or maybe barium titanate oxide. Okay. So structure phase transition occur. Okay. But there is another phase transition, that is magnetic phase transition. Actually, magnetic phase transition occur at a higher temperature, something like 500 degrees C. So, for example, in this mesoscale spectrum, or this is magnetic susceptibility, you see that at 500 degrees C, the magnetic phase transition from paramagnetic state to anti-ferromagnetic state occurs. More interestingly, the spin orientation switching occur at the structure phase transitions. So, in this region, actually, at high temperature, so in this, for example, 400 degrees C, in this region, the spins are located, oriented in the in plane, AB plane, as you can see here. But at 400 degrees C, the structure phase transitions, the spin orientation change into the direction parallel to the C-axis. Apparently, this spin orientation switching occur based on the structure phase transition I showed in the previous slide. Okay. Then this is another evidence for the spin orientation switching. In this case, we don't have a single crystals, but we actually oriented the powder sample by magnetic field. Then actually we found that the spin orientation occurs depending on the magnetic field applied. Okay. So now we are very sure that the spin orientation switching occur based on structure phase transitions. So what is happening? So we believe that what is happening is similar to the related to the molecular or single molecular magnet. In condensation chemistry field, this type of material shows spin orientation by changing ligand, in this case, this type of, I forgot which element, oxide and so on, you are able to control or change the direction of the spin moment. Okay, in this case, you have this up orientation. In this case, this direction. But of course, you cannot change the ligand. This is you have completely different material. But you can understand why in this case spins up and in this case spin line on. Okay. But here, what is happening is that as follows. So here, as I said, this is double layered perovskite. But as I said, in the case of perfect rigid octahedra, only oxygen, you can have this famous T2G triple degeneracy, and this is EG degeneracy. But here, high temperature, sorry. Okay, so this is the high temperature phase. So of course there is the one fluorine, different anion. So you can imagine that this type of the crystalline field splittings. But upon phase transition, structure phase transition, as I said, the very large octahedral distortion occurs. Then we can expect that these two orbitals are, reversed in positions, in energies. Okay, and yeah, so I think this is important, key feature for this spin orientation switchings. And Mike Van Bo, who is a theoretician, who is very famous for his prediction of the spin orientation in terms by using the HOMO-LUMO magnetic interactions using spin orbit coupling as perturbations. So I don't want to go into details, but his essence of his paper, his theory is that by investigating the highest occupied molecular orbitals, or for the orbitals, and the lowest occupied molecular orbitals. So by comparing or by calculating the L number difference, you can predict the orientation behaviors. Okay. So now, actually, based on this scenario or our orbital energy configurations, we are able to predict these spin configurations or explain these spin configurations. Okay. So I think in this regard, the control of the or control of the spin orientation can be chemically or explained or predicted by this type of simple considerations. Okay. And as I said, the molecular magnet is has been used for this type of concept has been used for this type of molecular magnet, but not for Mixed-Anion simple oxide materials. There are many materials in oxide showing spin orientation switching. The most famous one might be Moulin transitions in iron oxide. But in this case, the very complex interplay between crystalline shape and crystalline size and the surface magnetic anisotropy are involved. And in this particular, in this type of series of materials, the coupling between two magnetic sublattices are important. So for example, in this case, the iron sublattice and the rare earth sublattices are forming different spin orientations. The interactions between two can give rise to the spin orientations. Okay. But in our case, the simple consideration of the crystal structure can predict or explain the spin orientation switchings. All right, so this is the first part of my talk. The secondary.
Okay. Maybe
Yep.
I can ask audience if anyone have question on the first part. Please ask. Are there any questions, dear colleagues?
So maybe I can ask. So somehow I missed this.
Yes.
So you've showed the effect of magnetic field, right? So so how large the single ion anisotropy you would expect in this material. Probably theories calculated this.
No,
So basically, this effect is just the effect of single ion anisotropy, right? It's this one produced
single ion anisotropy.
Yeah. So have theories calculated this? This must be a very large effect, right? And whether this is consistent with the magnetic field effect that you have shown.
In this theory, I don't think they calculate, but actually this is no.
So this is only the qualitative explanation.
Yeah.
Okay.
So in our case, we don't calculate the actual magnetic anisotropies. Yeah. But in this type of measurement, I don't remember the magnitude of spins, but we are not able to switch the.
Yeah, not okay. So this is exactly was okay. My question. So you cannot really switch it by magnetic.
Yeah. Iron 3 plus is more or less.
Since it involves very large
isotropy. But
structural
in
energy.
this case, you can switch.
Okay.
Yeah.
Yeah, thank you.
Yeah.
Well, if possible, I'd like to ask also a little question about slide 12.
Which?
Slide number 12. Actually, the question is, you showed anion diffusion at some temperature, and I wanted to ask at which temperatures you observe this and compare to temperature of melting.
Anion diffusion.
Yeah.
Yeah, that depends, of course, on the materials itself. In this case, we observe the hydral diffusion at something like 300 degrees C or 400 degrees C. But in other material, we publish, for example, paper on hydride chloride material or hydride bromide material. This material show hydride conductivity at room temperature. So, yeah, it totally depends on the materials. But the important thing is that in this type of oxide material, the oxide is very hard and actually carrying 2 minus charge. So diffusion is more or less difficult. So that's why the 3 oxide furnace need higher temperature to activate. But in the case of oxyfluoride, if you are focused on the fluoride ion battery, the fluoride can be better in terms of the lowering the operating temperature. And that's why a lot of people are discussing or investigating the anion-based ion conductors, such as hydride-based conductors or fluoride-based conductors. And there are some papers, including ours. So basically, you can lower the operating temperature compared with the oxide materials. Is it okay?
Okay, thank you very much. Yeah.
Hiroshi, may I ask a question? Hiroshi, can I ask a question?
Yes, of course.
It looks similar to multiferroic material because you have active electric subsystem and active magnetic, and the temperature of this transition coincide. So the question is whether you can see multiferroic effects in this compound, like apply magnetic field and change the electric permittivity or vice versa, something like that, or not. Maybe not, I don't know. Looks similar to multiferroids.
Yeah.
But not exactly, probably.
Yeah, we observe this type of behavior, but we are not actually, the main problem is that we only have a powder sample, and of course we align the materials, but it's not perfect. So Yeah, we
But I
haven't.
think that it is first order transition at 400 Kelvin, and you can not influence it significantly by external magnetic field. It is hysteretic. So the first order transition at 400, right?
Yeah.
So probably it's almost impossible to influence it by external magnetic field.
For the electric properties,
I mean that it is not like in multiferroic when you apply magnetic field and change the electric permittivity. In this case, probably nothing like that will happen, simply because it is rigid first order transition.
But I agree. But
Structural transition.
major problem is that we only have a powder sample, and
I
it's not.
understand. Yeah. Okay.
Yeah.
Okay.
Yeah.
So
But
probably
maybe.
let us continue with lecture.
Yeah.
Okay, please.
Yeah. So this is the first part of my talk, and the second part is on vanadium. Sorry, this part, European vanadium O2H. But before starting to talk about this particular material, we'd like to talk about this material published by Mark Hayward in Oxford University. Actually, this material perovskite, certain material perovskite, but by using calcium hydride reduction, you are able to completely replace this apical oxygen top here by hydride anions. So this is another example of the anion ordered materials. So this is nothing but the reducing reaction. So the vanadium D1 state changes to D2. But this configuration very important or interesting because the starting materials three-dimensional, so nothing special. This is Pauli paramagnet. But after the reaction, this change into insulating state. And here, the D2 two electrons are occupied in this T2G state. The important thing is that the hydride is, at the apical side. So crystalline splitting, observed in this way. So here, the lowest occupied state are the XZ and YZ. So actually, this crystal field splittings makes this system a half-field state. So half-field state is very good for having the Mott insulating state. So by considering some electronic interactions, actually this material forms this type of band structures, and the Mott insulating state appear in these materials. Okay, so actually this is possible because of this anion order structures. Okay. Then, following this work, we actually prepare new material. This is the European-based vanadium oxide. So we actually do the nearly same reactions, and we obtain this isostructural materials. But in contrast to the previous material, strontium-based material, this material has the EU2+, which carry magnetic moment of the S equal 7/2. Okay. And we found that the vanadium, this material shows the very similar Mott insulating state or anti-ferromagnetic ordering state based on vanadium. But in addition, as I said, the EU2+ carry the magnetic moment, and actually this EU magnetic moment form the ferromagnetic order. Okay, and this ferromagnetic order transition temperature is about 10 Kelvin. The magnetic moment is comparable with our expectations. So now, based on in this material, two independent things is happening. This may be not so interesting, but we actually continue to study this material by growing the thin films, epitaxial thin films using the STO substrate. And this just show the successful preparation of this epitaxial thin films. Okay. But surprisingly, we obtained a very interesting change in lattice parameters. So here, I showed the film thickness, film thickness dependence of the lattice parameters. And this lattice parameter, the a-axis and c-axis, is based on the powder sample. Okay, as you can see, the both a-axis, in-plane axis, and the out-of-plane axis are reduced. Okay, that is quite unexpected because typically conventional thin films, when you apply compressive strain, then you have the increased out-of-plane distances. When you apply tensile strain, then the out-of-plane distance is reduced. Okay. But here, what we observe is that both in-plane and out-of-plane distances, parameters reduces, meaning that the negative Poisson ratio is observed. What is happening? So we actually found that this is due to the charge transfer from the EU layer to vanadium layers. So this can be understood in this way. So here, the originally the powder samples have the EU2+ state, but by applying the tensor, in this case we use an STO. Anyway, in this case of STO, the STO substrate can apply tensile strain. Okay, so this represents the vanadium T2G orbitals. So these T2G orbitals are squeezed. As a result, this empty dxy orbital become dispersive. And here, the EU4s state is located. And this, I believe that this is situated in between the vanadium HOMO band and the LUMO band. Okay. Then, by applying the tensile strain, as I said, this interaction, the overlapping between dxy orbitals are increased, making the dispersion of this empty band larger. Then at some point, this film level touches with this empty orbitals. Then electron charge transfer occur from this EU-based band to the vanadium-based band. Okay, and the the EU is now oxidized from 2+ state to 3+ state. And the 3+ state, of course, they have a smaller ionic radii. So this explains that you have the smaller lattice parameters. Okay, that is for the smaller out-of-plane lattice parameters. So I believe that this is the most reasonable explanations, namely inter-size charge transfer, reasonably explain the lattice shortening along A-axis and C-axis. Okay. Then actually this inter-size charge transfer drastically change the physical or magnetic properties. Firstly, the transition temperature, the ferromagnetic transition temperature for EU are greatly enhanced from 10 Kelvin for the powder sample to nearly 40 Kelvin for the 10 nanometer thick thin films. Okay, so enhancement of the TC is observed. Additionally, we found that this material show the very strong magnetic anisotropy. So EU2+ doesn't carry the orbital moment, so only S component exists. S equals 7/2. Okay. In this regard, like iron 3+, the magnetic anisotropy should not be so high. However, here, as you can see, in the same films, the magnetic anisotropy is very high. And also this is perpendicular magnetic anisotropy is observed. And based on this calculation, we found that this magnetic anisotropy energy is comparable to the neodymium, very famous permanent magnet. Okay. The origin of the magnetic anisotropy is still unclear, but there are some possibility as I show here, but maybe time is limited. I don't want to go into details. But I believe that the itineracy of the based on vanadium systems can couple with the EU magnetic moment and somehow explain induce such a gigantic magnetic anisotropies. Okay, so this is the second part of my talk. If you have some questions, I can have some answer.
Okay.
But,
Okay, please, if anyone have questions, you can now ask. If not, we will continue.
Yeah, may have once again one stupid question about why hydrogen here is -1, not +1.
yes. Actually, most of the people, including the solid chemists, work on the proton-based oxide materials. So this is protonic. But in this case, by controlling the synthetic, conditions, you are able to make hydrogen negative, H minus. So actually, I show in the previous slide the vanadium oxyhydride. So that for ammonia synthesis, and in this case, same. By controlling reaction conditions, which is very reductive conditions, you are able to.
Yeah, but just physically or chemically, so there is so it takes an additional electron. Simply, it is in some void, right? And it can accumulate an additional electron. Is this the reason? So the say ionic radii is allowed to be large. Is this the reason?
Sorry. Basically, you can think of the size of the hydride similar to oxide. So here, just I wanted to emphasize, it's not actual size of the hydride. Yeah, but actually, hydride is very soft anion. Basically, hydride, so when you go down the
Oh, you just have a hydride and that's it. Okay, I see. So you shouldn't consider it like a one isolated hydrogen. Okay, I see. It's just a layer of hydride and that's it. Okay, yeah, thanks so much. Yeah, I'm sorry for the stupid question. Yeah.
Okay, so let us continue.
Yes.
Okay.
So let me move on to this part. This is the bismuth-based oxyhalide or chloride materials. So as you might know, the oxide layer perovskite are diverse. Many examples like leucinate, titanate, and cuprates. But what about the fluoride-based materials? Actually, this is mostly limited to double layer, the bismuth 2O2. So now we have bismuth here. So it's double layer. The most of the layered, fluoride material are double layers. Okay, so this is understandable because in the first topic, the bismuth contain the lone pair electrons. So actually, these lone pair electrons favor such a double layer formations. And I don't want to go into the properties, but actually we discovered that this material show very nice water splittings by visible light. And since this first paper in JAX about 9 years ago, we published a lot of paper based on this bismuth-based or lead-based oxyhalide materials. Okay, but commonly, these material contain bismuth 2O2 layers. Okay, but there are one exception, that is this composition, 2141 compounds. Here, compare with this double layer, you just insert this metal M layer into here, then you got this composition. So now you can have 1, 2, 3 triple layered systems. Okay, but by changing this M site, Y, LA, and bismuth, you are able to control the conduction band height. Okay, that is of course very important for photocatalytic activities. Okay, so actually what is happening is that the structure phase transition occurs, depending on this species. And thanks to Artem Abakumov, my friend, who determined these two crystal structures. Actually, we found that this material, actually bismuth oxide layer, so outer layer, this bismuth oxygen layer, are stretched to break this 2D layer into double chains or single chains. And this can be understood by considering that this middle layer is kind of acting as a substrate in terms of thin films. So this middle layer, when it is changed from yttrium to lanthanum or bismuth, this middle layer expanded and applying the tensile strain to outer layer to form such a chain type structures. Okay. Then this can reasonably explain why this band, non-bonding band change into anti-bonding band. Okay. So this is explained simply by using this molecular orbital pictures. Then this is another atom, actually my PhD student from Moscow, and he actually investigated the solid solution between the lanthanum and bismuth. As I said, this one is greater than the yttrium, Y3 plus, but these two species are very similar in size. But somehow we obtained that a very interesting very complicated phase diagram between the lanthanum and the bismuth, and as a function temperature. Interestingly, we observe the tetragonal phase in between these chain structures. So somehow maybe these two phases, chain phases, compete somehow with respect to each other to somehow form the non-bond broken ideal square lattices. Okay. So now we are working on a lot of things, but maybe I'd like to add one more thing. This is serendipitous discovery. Actually, when we worked on this triple layer systems, we found the tiny impurity phases. Then we tried to identify these tiny impurity phases, and finally we found that this is this composition, 12, 70, and 2. And this actually the C-axis corresponding to this 6-layer fluoride structures. Okay, so I was very happy to see this new materials. However, after deeper structure analysis, once again including the very nice help from Artem Abakumov, we found that this is not a simple 6-layer structures, but a structure containing both fluoride layer and the rock-salt layer. So here, these blue parts are based on fluoride layers. So 1, 2, 3, 4, 5, 6. But here, the kind of one-dimensional rock-salt rods are inserted. And actually, this gives rise to this wavy nature of the electron diffraction patterns. Okay. Then we decided to make some chemistry to eliminate these rock-salt layers. Then we pay attention to, actually, we made this fluorine oxygen 211 2-to-1 substitution chemistry, and we intended to obtain the only fluoride 6-layer systems. And the diffraction pattern after this fluorination, anion exchange reactions, we get the perfect flat 6 layers. And we got the improved catalytic activity for organic molecule degradation reactions. But final structure is not the fluoride structures. But now, once again, we got the integral structure between fluoride structure and the rock-salt layers. But in this case, each layer stuck like this. Okay. Anyway, such an integral structure between rock-salt and fluoride are pretty rare. Maybe this is the first example. And the second example should be this type realized in these materials. Okay, it's very complex structures, but in this chapter, I'd like to focus. Main message is that by using this middle layer and considering it as a kind of substrate to apply the strain, you are able to control the crystal structure to form the zigzag chains, and this can change the band structures. So this is the third part of my talk. Is it maybe complicated? But finally, I'd like to show this one. So recently, actually last year, I published a paper on the review article on this type of the bismuth-based oxy highlight materials. Today, I just focus on this concept G, which is internal strain. Okay, but there are many other factors which it's important to control the conduction band and the valence band and so on. So maybe this can give you the brief summary of this type of materials in terms of the controlling the band structures. Okay, so this is my third part of my talk. It's okay. Any questions?
If there are any questions, please ask. If not, we will continue.
Yes. Okay.
Okay. Okay.
So it's okay. So this is the last part of my talk.
Okay.
So here, it's once again, it's unexpected discovery. But before going to my main conclusion, I'd like to discuss the conventional topochemical reactions. As you know, topochemical reaction is a reaction where there is structure similarities. The maybe most famous example is that this graphite material showing the lithium intercalations. You can check easily by X-ray diffractions. Okay, this is another example. Actually, this is my my paper. So here, this perovskite structure change into the so-called infinite layer structure. So here, that cubic to tetragonal phase transition can be easily detected by X-ray diffractions. For example, this 110 of the cubic phase split into 110 and 101. Okay, in this way, the simple powder diffraction can allow us to solve a crystal structure, which is very difficult in general in conventional materials. But topochemical reactions, you are able to solve the crystal structure pretty easily. But in this material, my former student worked on this material for ammonia catalysts, as I mentioned in the beginning of my talk. But this material discovered by Frank DiSalvo, who passed away last year. And but this material shows very high ammonia synthesis catalytic activities. But after these catalytic reactions, we found that the crystal structure of this one completely changed into hexagonal one. So here, this is the orthorhombic structure changed into hexagonal one. The question is, can you imagine the crystal structure of the final materials? Okay, which we couldn't. Okay, so that is very difficult. And actually, we initially thought that this material completely changed into completely different crystal structures. However, once again, the famous Russian crystallographer helped me greatly, and actually we found that this material, crystal structure of the material after ammonia catalyst reactions. And this is how crystal structure look like. This is hexagonal. You can see that this octahedral chains are running perpendicular to the parallel to the c-axis. Additionally, we found that the hydride is not proton, it's H minus, positioned at this octahedral void surrounded by 6 calcium atoms. So calcium is highly electropositive. So surrounded by 6 calcium, the inside octahedral center should be favored by the negatively charged species. That's why the hydride is located here. But apparently, this crystal structure very, different. Okay, but this is topochemical reactions. So here I just try to show that how the crystal structure changed from orthorhombic structure to this hexagonal structures. The final structure has one-dimensional octahedral chain, phase sharing of octahedral chains. But here, the starting structure has locks out one-dimensional block, right, running perpendicular to the slide. Okay. But these blue parts are completely different. But you see that these parts are bridged by chromium N3 units. Okay. Then these structure can be converted from one to the other by rotating this hexagonal unit or maybe this triangular unit to form in this way. In this sense, that this material has rotational structure transformations. Okay, so you may like maybe think that this is the mimicking the hinged tessellation movement. Okay, so anyway, this is topochemical reactions, and this transformation by hydride insertion can be partly rationalized by this scheme. Actually, the chromium 3 plus, the chromium N3 carry 3D electrons. And the crystal field splitting picture is shown in this way. But after the hydride insertion, which is nothing but the oxidation reactions, you can remove one electron from this highest occupied orbitals. Then this can have some stabilization, provides structure, electronic stabilization of this final crystal structure. Okay. Then maybe we may just omit this one, though this shows nice, interesting the mechanism for ammonia catalysis. And my student continued to this work by substituting the calcium site by strontium. But in this case, without insertion of the hydride, you are able to switch this orthorhombic structure to hexagonal structure. Okay. Upon 30% doping, this material, without changing composition, this material is changed into hexagonal structures. But this is isostructure substitution, calcium 2 plus, strontium 2 plus. But self-redox reaction occurring in these systems. Namely, in a final hexagonal structure, once again, the negatively charged species is located here. Instead of hydride here, but hydride in the previous material, this material contains electron. So this is electrolyte materials. Then as a result, the chromium 3 plus oxidized into chromium 4 plus. So self-redox reaction occurs despite we are carrying out the isovalent substitutions. Okay, and actually this is very unusual when we look into the electrolyte studies. Maybe this is the very famous example. Sodium can be transparent or insulating when you apply the external pressure. Okay, this is because the sodium electronegativity of sodium becomes negative when you apply extremely high pressure. The negative electronegativity means that the sodium, elemental sodium, doesn't want to carry electron. He wants to provide the electron to other species. And that's why this material forms the ionic compounds between the sodium plus and the E minus. Okay. This is one example, but there are many other examples where the high pressure, applying high pressure induces the formation of the electrolyte materials. Okay. But here, what I showed in the previous slide is that the strontium substitution is the negative, nothing but negative chemical pressure. But somehow that this material shows the electrolyte properties. So electrolyte is induced by, in this case, negative chemical pressures. And this is the theoretical calculation, TFC calculation for this material. And this band corresponding to the band for based on the electrolyte in these octahedral voids. Okay, so this is the final part of my talk, and this is the just the summary of my 4 chapters. But there are many things we are carrying out, and today I just focusing on the band structure and so on. But this is the the work we are carrying out recently. So this is another example, the unexpected or unusual topochemical reactions. So here, this is the figure 1, hopefully. But this one showing that the individual layers are changing to other layers. For example, here, octahedral layer, each layer, octahedral layer changing to pyramidal layer and the square planar layers. So actually, this is oxygen extractions or anion substitutions. In this case, only coordination geometry change. Okay, but here, sorry, I don't want to show the compositions, but here the double tetrahedral layers, double tetrahedral layers change into single octahedral layers. So somehow you can change the crystal structures much more drastically than we can expect. Okay, so I hope that you may have such as diverse chemical reactions for some nice functions. Okay, so finally, I'd like to just maybe introduce this conference, which I chair. I'm a chairperson of these conferences. I'm organizing the Second International Symposium on solid chemistry, solid chemistry in Shimane, which is my hometown. And we have currently successfully got 26 or 25 invited speakers. We want to have some more. And yeah, and this is maybe you remember that actually this is not in Kyoto, this is in Shimane, so which is my hometown. Actually, Professor Alexander Baziliev visited this place many years ago. And this is my hometown. And this shrine has this fun, so this is based on Izumo Shrine things. And about 22 years ago, we spent some time in my hometown, and we had this nice photos.
Nice dress.
Nice rest. Right. So if you are able to join us, yeah, I'm really, so, you are welcome. And finally, I'd like to thank all my colleagues. We had a very nice 15 years anniversary party a few months ago. We had nice colleagues, including international, students and so on. And finally, I'd like to thank the audience in this talk. Thank you very much.